today's experiment, we'll be using our knowledge of solubility to determine the identity of a set of unknowns. Goals. We're going to make qualitative observations of what happens when we mix two unknown substances together by recording color, pH, odor, and formation of a precipitate. Qualitative chemical analysis. Qualitative analysis is the process of identifying the elements or group of elements in a substance. Qualitative analysis does not include the use of numerical measurement. Instead, it relies on your powers of observation and note-taking to collect data. This data includes colors, smells, pH, or appearance of a solid, information you will need to write down in your lab notebook as you work. Then, when you go home and try to identify unknowns based on your observations, you'll need to take an analytical approach, that is, work methodologically to analyze your results. The lab manual contains vital information needed to help you understand some of your qualitative observations, including a list of facts about some of the solutions we're working with, and instructions on how to correctly test the pH of a solution when trying to record its pH. You'll also find a copy of the solubility table in the appendix at the end of the lab manual. Chemical reactions. Solubility. The formation of a solid substance as part of a chemical reaction can be predicted based on the solubility of the product formed. We think about solubility fairly generally as the ability for a substance to be dissolved or form a homogeneous mixture in water, that is, be soluble or insoluble. Remember, when a substance is insoluble, you will observe a solid form in the solution. We can predict whether or not a substance will dissolve in water based on a series of guidelines, which we'll discuss a little bit further. What we're looking for then is how the solute behaves when dissolved in a solvent like water. As a solute becomes surrounded by solvent molecules, the substance is said to have dissolved. If we look at an ionic solute, as the solute is mixed with water, the ionic solute may break apart into individual ions, becoming dissolved. On the other hand, some ionic solutes do not break apart water into ions and thus do not dissolve. Those are called insoluble as they form a solid precipitate. When substances react with each other when you mix them, some will form soluble substances, which will dissolve in solution, and some will form insoluble substances, which are the solid precipitates that form at the bottom of your solution. Overall equations. A molecular reaction is one that simply shows the substances and phases involved in a chemical reaction and their stoichiometry. You may hear these reactions called the overall balanced chemical equation, the molecular reaction, or the total reaction or chemical reaction. When we talk about a balanced chemical reaction, we are referring to the molecular equation. For example, we use lead-2 nitrate reacting with 2 sodium chloride to form lead-2 chloride, a solid, and 2 sodium nitrates. I've shown the balanced chemical reaction there on the screen. You should notice that each of the substances have their phase indicated, whether it's aqueous, that is dissolved in water, or form a solid, as is the case with the lead-2 chloride, which is a solid. But you can also have liquids or gases. Ionic equations. The ionic equation shows all the ions that are present in the solution. If you think about taking the starting materials, lead-2 nitrate and sodium chloride, and mixing these aqueous solutions in a beaker, what ions are going to be present? We know that lead-2 nitrate is an ionic compound, so it'll break apart in its 2 ions in solution, Pb2+ and NO3-. We'll list those in the ionic reaction. Sodium chloride is also an ionic compound that will dissolve or break apart in solution, forming Na+ and Cl-. On the other side, once this reaction occurs, we will have the nitrate ions, the sodium ions, but now lead-2 chloride will form, which is insoluble in water, so we'll indicate that with the S for solid. Net ionic equations. Net ionic equations are simplified ionic equations, where the spectator ions are removed. This allows us to focus solely on the ions that are participating in the chemical reaction, often forming a solid precipitate. So if we look back at the ionic equation we just wrote, if a substance appears on both sides of the arrow that hasn't changed, then it is a spectator and we can cross it out. What's left then, we will rewrite and put into the net ionic equation. That gives us lead-2 aqueous plus 2 chloride ions in aqueous solution forms lead-2 chloride, a solid. Let's look at an example. What is the net ionic equation for the reaction of sodium carbonate and magnesium chloride? Let's first start by writing the balanced chemical reaction. Since we are reacting two ionic aqueous solutions, we know that the reaction will be a double displacement reaction. Na2CO3 plus MgCl2 goes to form, here we're swapping the ions, NaCl plus MgCO3. We also need to write in the phases. As we're told that in the question, the solutions are aqueous. These first two will be aqueous, AQ, and then we have to determine the solubility of the other two. We know from the solubility rules, and likely some of our own personal experience, sodium chloride or table salt is soluble in water. So I'll write AQ here. Magnesium carbonate, that will need to refer to the solubility table for. In the solubility guidelines in the lab manual, we can see that the carbonates are insoluble in water and doesn't follow the exception, as magnesium is not an alkali metal. So we'll need to write that it forms a solid S. Okay, now we need to break down the balanced chemical reaction into the full ionic equation. So all the aqueous substances will break apart into their respective ions. We will write Na plus aqueous plus CO3 2 minus aqueous plus Mg 2 plus aqueous plus Cl minus aqueous goes to form Na plus aqueous plus Cl minus aqueous plus MgCO3 solid. Okay, now that we have the full ionic equation, we need to determine which ions are participating in the reaction and which are not. So I'm going to look at the products on the right and figure out which one forms a solid. In this case, that's the magnesium carbonate, MgCO3, since we denoted it as in the solid phase. Now I look to see what the ions were that produced the product, in this case, the magnesium 2 plus and the carbonate 3 minus, and I'll write them down as the reactants with their phases. Thus, to double check, I'm going to look at the full ionic reaction to see if the ions that are left are the same on the reactant and the product side. Since they are, I'll leave them out, and I've got my net ionic equation. Experimental techniques. Success in lab this week will be based on your powers of observation and ability to collect useful qualitative data, specifically determining pH using litmus paper, changes in odor or smell, the formation of the solid, and color changes. We also need to address how you will organize your data a bit. First, we'll be using litmus paper to determine whether the substance is an acid or base or a neutral pH. Litmus paper comes in two types: red, which stays red when placed in acids, and blue, which stays blue in bases. So if we dip our litmus paper in an acidic solution, you'll see that the acid paper on the right stays red, while the blue litmus paper on the left turns red. If the litmus paper is dipped in a neutral pH solution, neither of the papers change colors. But if you dip the acid paper on the right in a basic solution, the litmus paper turns blue, while the blue litmus paper on the left remains blue. You will also need to be paying attention for a change in odor. When some substances are mixed together, they can give off a variety of distinctive smells, and likely you've smelt some of them before. The change in smell is very specific. For instance, the smell of rotten eggs comes from the formation of hydrogen sulfide, HS. This gas is very distinctive and likely you'll quickly recognize it. Another smell, that of ammonia, you've likely smelled around your home as it's a common cleaning reagent. If you smell that, you know you formed ammonia gas. Yes, solubility will be one of the things we're observing. You need to keep an eye out for the formation of a solid, also called a precipitate, in your wells. Color changes are just like they sound. You'll see the color of your solution changed as it's mixed with another substance in the solution. The lab manual contains a list of helpful facts about the solubility of substances we're working with. Use them to figure out what the unknowns are based on what your observations are. You may notice the first fact given tells you a lot about one substance in particular. You are going to use this list in conjunction with solubility rules in the appendix of the lab manual to figure out which substances are the unknowns based on your qualitative observations and how the solubility rules predict the reactions will occur. To keep your data organized, draw a table like is shown in the lab manual in your lab notebook, making sure to make the table large enough that you can write in it. You may want to break down the table over a couple of different pages just so you have enough room to write. As you mix your solutions, write your data down in the appropriate cell. Notice that when using a table like this, you'll use only half of the cells. The other half will be empty. The well placed lists we use do not have 10 rows, only 8. So you will need to make some adaptations. So you're going to need to use two of the columns on the right that aren't used to test solutions to test I and J against the other unknowns. Experimental notes. Reminders. Be systematic in the way you approach mixing the solutions. Only mix one at a time so you can identify an odor if it appears. Keep your solutions organized. Label the well plate, then add solutions to the corresponding well one at a time. Write your observations down in the matrix you draw in your lab notebook that matches how the well plate is set up. Make sure you leave yourself plenty of room to write, so feel free to let your metrics take up a full page or more in your lab notebook. Make sure you are washing the well plates before you start. It's a good laboratory practice to never assume the well plates or any glassware is clean in the lab. Always wash your equipment before you start. For the well plates, you'll want to use a Q-tip and soap and water to get each well nice and clean and scrub them down before you start and after you finish. Make sure you look over your data before you leave. Once you leave, you won't be able to come back and redo a test, so make sure you have clearly written down your observations and are sure of your results. Waste disposal. For lab this week, your solid waste, like empty plastic pipettes and pH paper, can go into the garbage can. Any reacted liquid reagents and excess unknown solutions must be poured in the waste container fume hood. The semi-micro test tubes that you used and emptied must be placed in the broken glass container. Please double check before you pour your waste into the waste container that the funnel is open or in the up position as shown on the left and not closed as shown on the right. When multiple students pour waste into the closed lid of the funnel, it becomes not only a safety hazard for others in the lab, but also a serious safety hazard that has resulted in injury of our personnel preparing your labs. Hints for success. Stay organized. You're going to collect a lot of information across all 10 solutions, so you'll need to rely on the information you record in your lab notebook and the matrix for each substance. After lab, when you start to try to determine what the unknowns are, you're going to use deductive reasoning. That means you'll need to pull together what you observed about the solution and what's given in the lab manual as hints and advice and the solubility rules.
If you have any questions, please reach out to your teaching assistant, speak with the TA in the General Chemistry Learning Center in Jacobs Science Building, room 219, or send me an email.